Plus, immediate funding for NOVA is provided by the Park Foundation.
We see teacher behavior. We see kids reaching their potential. It's what inspires us to create software that helps you reach yours.
Science has given us the framework to help make wireless communications clear. Sprint is proud to support NOVA.
Funding for the Albert Universe is provided by the Albert P. Sloan Foundation to enhance public understanding of science and technology. And by the National Science Foundation, America's investment in the future. Additional funding is provided by the George D. Smith Fund and the U.S. Department of Energy, fostering science and security. Major funding for NOVA is also provided by the Corporation for Public Broadcasting.
We are PBS.
Quantum laser pointers brings you the infamous double slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. The laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. The surprising result, light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Now, blackbody radiation is a very interesting and powerful idea, but moreover, it can be understood with relatively simple ideas. So let's begin with a nice thought experiment. Imagine a box floating in space, far away from anything, out there in the vast nothingness of space. Now recall that throughout all the space, there is the light radiation left over from the Big Bang. It is this that we measure when we look at cosmic microwave background radiation. So as the box is floating out in space, some of the leftover light will be falling on the box and hitting it. The box can either reflect the light or it can absorb the light radiation. Now a black box will absorb all the light that falls upon it, and that's what makes things seem black. They reflect very little light and absorb all the light that hits it. Now a white box or one covered in mirrors would reflect all of the light. So now let's consider that black box. The cosmic background radiation will be falling upon it constantly, being absorbed and heating up the box. Now the temperature of the background radiation is about 3 Kelvin, so if the box is about 3 Kelvin, then what will happen? Will it still continue to heat up? Like I said, radiation will be falling upon it, heating up constantly, and if it doesn't have a wave going down, then it will heat up forever, without any good way to cool off, then given enough time to become hotter than the sun. This really doesn't seem right, so we need some kind of mechanism to cool off the box, because the radiation will just continue to heat up the box. Well, in everyday life, something hot means it's heat out into the surroundings, into the air and into objects that it's touching. But in space this can't happen because there's nothing to transfer the heat to. But there is something that easily propagates through space and carries energy, light radiation. And light carries energy, and every single wavelength carries different energy. And so we can suggest that this is how the box will try to keep a thermal equilibrium with its surroundings. That is to stay about the same temperature. Well, with this in mind, let's try to consider how we can cool the box down with this idea. We could have it emit light at all wavelengths of energies with different amounts of each wavelength to carry heat away. This leads to the idea of a perfect black body. The black body will absorb all radiation that falls upon it, otherwise it just won't be black. But as a result, it must perfectly emit all radiation too, otherwise it will just heat up. Now this is an interesting idea, but it seems a bit weird. But you can see it for yourself at home if you have anything that uses electricity to heat up objects, electric grills, electric heaters. If you leave it on for a while, you see it starts to glow red. This is because it is emitting red radiation to cool off, and so to stay at a steady state. Similarly, if you see a lump of coal on fire, it glows red. This is again because its temperature is quite high, so it's emitting radiation to cool off, and enough red radiation is being emitted to be seen. This is also the idea behind how thermal imaging works. An object will emit radiation related to its temperature, and thus things about room temperature mostly in the infrared spectrum. As things get hotter, they will eventually emit most light in the visible spectrum, and if they get hotter still, they will mostly emit ultraviolet radiation. Going back to electric heaters, a black body emits enough red radiation to be seen at about 600 Celsius or about 900 Kelvin. Temperatures far above what we see in everyday life, so it stands to reason we don't normally experience black body radiation. Now, a physicist called Max Planck found a way to describe how much light radiation is emitted from a hot object, but more importantly, how much energy is emitted for a given temperature. So let's briefly look at the graph, discuss the properties of it, and try to see what they also mean. This way we can get a better understanding of what black body radiation actually tells us. You may want to recall that the energy of a photon is proportional to the inverse of its wavelength, so that the smaller the wavelength, the larger the energy, the smaller the energy, the longer the length. Now, visible light has a wavelength of about 0.1 to 0.7 micrometers, which is a very small part of the spectrum as shown. You can easily see that we can't see a lot of the light emitted, especially at low temperatures. Next, we can see that the low wavelengths, that is very high energies. Very little light is given off beyond the peak, with a very sharp fall after the peak, especially when the objects are very hot. Whereas at low temperatures, there's a smooth curve going down. Another important point is that as the temperature gets hotter, the peak moves to shorter and shorter wavelengths. That is, the object starts emitting most of the light at really, really high energies. And this point is important because it will come back to prove very useful later on. We can also see that for higher wavelengths of light, there's a slow decay towards the thing being emitted, and no matter what the temperature is about, the same amount of low energy light is emitted. Also, the peak gets sharper when we increase the temperature. This is why we can see red at about 600 Celsius, even though its peak is still well before red, which is about 3000 Kelvin. The peak is wide enough that red light will have enough emission even below 300 Kelvin to be picked up in the dark. Finally, the total energy emitted is proportional to the area under the graph, and we can notice that this increases as the temperature increases. This fits with our idea of a black body emitting enough radiation not to really heat up. Okay, now you may be thinking that why bother with your time with this, and why have I told it about at all, and why is this even important? Well, give an example of just how useful black body radiation is. Stars. If you were to look at the emission spectrum from a star, you'd see that its curve approximately matches our fine black body formula. And so we can model stars as black bodies. Let us try this with the sun. We can look at its spectrum and see that it's about 6,000 Celsius. Then if we go and measure the temperature of the sun, we find the same thing. It turns out it's about 5,778 Kelvin. Close enough. Moreover, this explains why the sun is white. Its peak is in the middle of the visible spectrum. The visible spectrum is about 400 to 700 nanometers. And so, because it's at lowest temperature, its peak is white and it emits a lot of light across all the visible spectrum. And so we see all the colours of visible light. And as a result, it appears white. So let us take a brief detour and think about what we can do with this in other fields of science. And I'm going to consider evolution. If an eye wants to be able to see at its best, then it needs to take advantage of the main source of light around it. And everyday light, that would be the sun. But the sun emits most of the light around its peak. So if an eye was to evolve to use the sun, it makes sense that the peak of the sun would be in the middle of the visible spectrum. If not, our visible spectrum would shift, such that the peak is now in the middle. This allows us to formulate a hypothesis that if light was to form around a star with a significantly shifted peak, if it was to evolve some eyes, they would see it around the new peak spectrum. Now back to physics for the final run. With this new knowledge of black body radiation, we can look at the main sequence stars far away and see what colour it is, and then we can work out its temperature solely from its colour. 61 Cygni A is red, so its temperature would be about 4,500 degrees. Whereas Pi Andromedae is blue, so we expect its temperature to be about 15,000 Kelvin. If you don't feel like this is impressive enough, well, knowing how hot it is, we can also work out how much fusion is needed to take place in order to keep it at this temperature. And in order to have this much fusion, we can then work out how much mass has to be there. The final consequence is that we then know how big the star is. If you think this is interesting and you'd like to know a bit more about it, then you should look up Kurzman Russell diagrams. What would this show? What it does is show how this can be used to classify stars using the size, the temperature, the colour, to be able to say how big, how bright, what type of star any star is. Finally, the last thing I want to just briefly touch upon is how this is related to quantum mechanics. Max Planck came up with the solution to black body radiation, whereas classical mechanics could not predict it. Classical mechanics can only deal with the low energy part of the emission, but not the high. And this was known as the ultraviolet catastrophe. In order to fix this, Max Planck suggested that light was emitted by the atoms in a black body in small packets of energy called quantum, which then went on to become known as photons. This is a radical difference from classical mechanics, which predicts the continuous emission of energy, not just in small discrete packets. And this was one of the first pieces of evidence for quantum mechanics, as it relied upon energy coming in discrete packets of energy, essential concepts of quantum mechanics. Secondly, if we were to look at the emission spectrum for the sun, we can see that the actual emission is very shaky. This is to be expected as the sun isn't the perfect black body. But there are wavelengths where the intensity seems to drop a lot. These are from quantum mechanical effects, and these are some of the best evidence for the current model of the atom. Thank you for listening. Please let me know what you think. And for my next video, I'm either going to take a small departure into basic population dynamics or into the meter quantum mechanics yourself. If you have any preferences, please let me know.
Quantum laser pointers brings you the infamous double-slit experiment, right next to Palm. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. The laser shines a coherent beam of light into a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passing through the parallel slits, not as particle, but as waves.
Visit our website or subscribe to our YouTube channel now. We have among the first to see our free line of double-slit lasers, quantum laser pointers.
In our search to find out what is actually happening at that point in empty space, outside the magnet, we have learned a lot. We have discovered that empty space is a complex entity. It can be stretched, as seen in the external universe. It can be bent, as understood by general relativity. It's filled with various types of matter fields, force fields, and the Higgs field, according to the Standard Model. The elements of these fields are quantized, massless, and almost energyless. And we know that empty space offers resistance to change in these fields, for example, permittivity and permeability. We know that with enough energy, the elements of a field can bunch up into localized particles with properties like mass, spin, and various types of charges that spew out their own field elements into the empty space around them. But as much as we've discovered, it feels like we're still just scratching the surface. The order in the Standard Model, like the order in the periodic table of the elements, lends itself to the theory that there is an underlying structure yet to be discovered. This, along with the mysteries of dark matter and dark energy, plus the fundamental incompatibilities with general relativity, also speak to a deeper reality. String theory, supersymmetry, and loop quantum gravity are just a few of the candidate theories currently being explored. In that vein, as we approach the end of our How Small Is It video book, we'll take a look at the smallest that small can get. In quantum mechanics, there is a minimum length called the Planck length. It is over 62 trillion times smaller than a neutrino, our smallest elementary particle. This Planck length is as many times smaller than this dot, as this dot is smaller than the physical universe. Theoretically, it is impossible to determine the difference between two locations less than one Planck length apart. This idea takes us back to our first segment on the microscopic, where we saw how light diffraction created the same problem for optical microscopes. As we pointed out at the start of our story, you can't probe a grain of sand with your finger. How are we going to find out what's happening at this Planck level, the level where the quantized field elements operate? This is just one of the many challenges for physicists of tomorrow. It should be interesting. Let's take a look at the credit segment. It will point to other resources for additional research. Thank you for watching.
QuantumLaserPointers.com.
Quantum laser pointers brings you the infamous double-slit experiment, right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. The laser shines a coherent beam of light through a film disc containing two parallel slits. Light strikes striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves. When the peaks of two waves overlap, it creates a band of light. When the peak of one wave meets the valley of another, light is canceled out. Variations of this experiment spurred public debates between Albert Einstein and Niels Bohr on the true nature of reality. It's been called the granddaddy of all quantum weirdness. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers. QuantumLaserPointers.com.
Is reality real? Or can we be living in a sophisticated simulation? Will the universe be more like a dream than we ever imagined? How can science help us answer these questions? Welcome to the simulation hypothesis.
Have you ever had a dream, Theo, that you were so sure was real? What if you wanted to look from that dream? How would you know the difference between the dream world and the real world? What if you woke up one day and discovered that everything you've always taken for granted is not what it seems at all? What you thought was reality is actually a simulation, a very complex, sophisticated illusion that you live inside of. Even solid matter itself is no more real than, say, a rock that you would pick up in a dream. And not only are you living in a simulation, but it's being generated by a system that you can contact with your mind and actually change the simulation itself. In effect, hacking the universe. What would you do to change the world? Well, recent scientific discoveries are strongly suggesting that this is the case, that we live inside a simulation, and that we, as observers, have a demonstrable power over it. We are actually participating in the creation of the reality that we live in. Wait, what? Are we really living in a simulation? Well, this is the conclusion that physicists and cosmologists have been coming to, and although this idea would have been ridiculed in the recent past, it is now being taken very seriously. Cutting-edge physics experiments have been producing some very strange results. Results that our universe isn't an objective reality, but that it's actually emerging from something else, something non-physical and beyond our senses. In the digital age, science is beginning to see a correlation between our world and the world of a virtual reality.
The Matrix is everywhere. It is all around us. Even now, in this very room. You can see it when you look out your window or when you're television.
Plato versus Democritus. What do these guys have to do with anything? I thought we were talking about science, not philosophy. Well, all scientific inquiries are based on one or more philosophical positions. So let's quickly go over some of the philosophical arguments that different scientific approaches are built upon. Ancient Greek philosophers already had the basic idea of the atom, and they used this idea to help them explain how reality worked. Out of all their various conversations, several very different views emerged. These views are best expressed in the works of Plato and Democritus. Democritus built his philosophy of materialism on the assumption that atoms are eternal, indestructible, and are the only things that really exist. All other things exist, said Democritus, only because they are composed of atoms. Following this logic leads you to believe that consciousness is a product of physical processes in the brain. This is the philosophical assumption that Isaac Newton, Charles Darwin, and most Western scientists until very recently built their work on. Plato built his philosophy of idealism on the assumption that the basic underlying structure of everything isn't the atom, but abstract mental forms that determine an object's properties. Plato believed that ideas are more fundamental than objects. For instance, a perfect or ideal sphere exists only as an abstract mental form, or idea. Any sphere that we see in the world, like a basketball, is simply an approximation of the ideal sphere. By following this logic, you come to believe that consciousness is primary, and gives rise to all physical matter and process. In other words, everything begins with consciousness, and there is a mind behind what we experience as physical matter. In much the same way that when you dream, your mind is creating a physical experience for you while you sleep. As you can see, these philosophies are mutually exclusive, and are in fact opposites. Both cannot be true. Either mind gives rise to matter, or matter gives rise to mind. It's a very, very old debate, but science has finally harnessed enough power to settle it once and for all. The scientific hypothesis that our world is virtual, or dreamlike, has been explored in depth by many scientists, including Dr. Brian Whitworth. He took the two opposing views, one being materialism, that our universe is entirely physical, exists in and of itself, and needs nothing outside of it to explain it, and the other being the simulation hypothesis, that our universe exists as a virtual construct, and depends on information processing happening outside of space-time. Dr. Whitworth looked at all the facts that have been gathered from experimental results and asked which of you better fits these facts. After a thorough analysis, his conclusion was that the data much better fits the simulation hypothesis.
Right now, we're inside a computer program.
Scientifically, our universe simply makes more sense when viewed as a virtual construct emerging from consciousness, rather than simply matter existing independently of the mind.
This isn't real. What is real? How do you define real?
The analysis starts at the beginning, with the Big Bang. This well-established cosmological model demonstrates that space-time was created by a single event billions of years ago and expanded into what we see around us today. Nearly all scientists agree that our universe began to exist at one point in the distant past. From a materialist view that our universe is all there is, as an objective, independent reality, the fact that the Big Bang came from nothing is very hard to explain. How could everything come from nothing? But if you look at the universe as a virtual construct, the Big Bang model works perfectly. Virtual worlds always begin with an information influx from a zero state, since they need to initially boot up. Every time a computer game starts up, a Big Bang occurs from the perspective of the game. From inside the virtual world itself, the creation always comes from nothing, because before it boots up, there is no space or time as defined by the rules of that virtual world. Another thing to consider is quantum bits. The fact that light is quantized as photons, electricity as electrons, etc., better fits the hypothesis that we live in a virtual construct. Because in digital processing, all data must have a minimal quantity represented by bits or pixels, and our world displays the same property. Every computer-generated image breaks down into pixels when examined closely, and this is what science has found in nature. In the past century, physicists have discovered that matter really is quantized, composed of fundamental, indivisible particles billions of times smaller than an atom. And as science has discovered more and more about the way the universe behaves, it has become clear that nature is a matrix of computable bits. Space is quantized, time is quantized, energy is quantized, everything is made of individual bits, which means the universe has a finite number of components, which means it has a finite number of states, which means it's computable. If the true nature of the universe is indeed digital, that we do in fact have quantum bits of space and time, and that there's nothing that you cannot compute, and at the moment there is no evidence against this, then it's entirely consistent with the simulation hypothesis. Well, how does living in a virtual reality benefit me? Do I get superpowers? Can reality be hacked? Can we program nature and take control of our experience? Are we, in a sense, already doing this, but simply unaware of it? Okay, for the sake of argument, let's say the data does fit the simulation hypothesis better than it fits materialism. That's all well and good. But is there any solid evidence of computer programming in nature? It seems there is. Theoretical physicist James Gates has actually found computer code hidden deeply in the equations that describe supersymmetry.
So you're saying as you dig deeper, you find computer code writ in the fabric of the cosmos?
Into the equations that we want to use to describe the cosmos, yes.
Computer code,
Strings of bits of ones and zeros.
it's not just sort of resembles computer code. You're saying it is computer code.
It's not even just is computer code. It's a special kind of computer code that was invented by a scientist named Claude Shannon in the 1940s.
So are you saying we're all just, there's some entity that programmed the universe, and we're just expressions of their code?
Consider the fact of a maximum speed in nature, the speed of light. In 2011, scientists reported neutrinos traveling faster than the speed of light, but those findings were retracted when it was discovered that equipment used in the experiment was faulty. Nothing has ever been seen to travel faster than the speed of light. Nature has a maximum speed, and events in the virtual world would also obey a maximum speed since they would be limited by a finite processor. There's also the curving of space by massive objects and time dilation at very high speeds. Both phenomena correlate to virtual processing load effects. High matter concentrations in our universe may constitute a high processing demand, such that massive objects would slow down the information processing of space-time, similar to the way that high data demands in a computer will slow down the processing speed. Every digital symbol created by the same program is identical to every other in the same class. In computing terms, objects are simply instances of a general class. The fact that all quantum objects are identical in each class, photon, electron, etc., correlates to a digital equivalent, since in a virtual world, every digital object created by the same code is identical. While the objects we see in our world have individual properties, the quantum bits that they are built from are all pressed from identical molds. The simulation hypothesis suggests that this is the case because each bit is created by the same program. Taken together, all of this might constitute what the courts refer to as sufficient weight of evidence, favoring idealism in the simulation hypothesis over materialism. When coincidences continue to pile up and combine with explanatory power, it presents a very strong plausibility argument, or even a proof. But even more convincing evidence is provided by cases that the simulation hypothesis can easily explain, but which materialist models have tremendous difficulty with. One such case is non-locality.
Toto, I have a feeling we're not in Kansas anymore.
For materialism to be true, and the world to exist independently of mind, the concept of locality is necessary. This means that for objects to interact, they must be in close proximity. This is what Albert Einstein believed for most of his life. To understand quantum entanglement and non-locality, we should take a look at Einstein's life and his role in the development of quantum mechanics. In 1905, horses still mingled with cars in the street, Ty Cobb was a major league rookie, and Albert Einstein was a low-ranking clerk in the Swiss Patent Office. That year, in his spare time, he wrote 4 remarkable scientific papers. The first established the photon as the particle associated with light, overturning many years of understanding light as a purely wave-like phenomenon. He used this new description of light to explain the photoelectric effect. In another paper, he mathematically proved the existence of atoms, something that was still